Hi, hello. If you're new to the channel, welcome, and if you've been here before, welcome back. Now, it's been a few weeks since I last posted about the grey wagtail and about narrowboating. And it's not because I've lost interest in narrowboats and boating, it's because I've been busy with other projects and also with some family issues and commitments. Hence the break in posting. In this video, I will look at the electrics on board the grey wagtail because, as several comments have pointed out, I need to understand how they work, or it will lead to ruined batteries, which could prove to be very, very expensive indeed. In the video, I will try to remember my schoolboy physics and wrestle with the ideas of direct and alternating currents, parallel and series circuits, amps, volts, watts and amp hours. What, pun intended, could possibly go wrong. But don't worry, I won't spend too much time on the physics, so please keep watching. Now, along the way, I'm bound to get things wrong. When I do, please let me know in the comments and include the time point in the video where I made the mistake. I will then add the mistake to my pinned comment of errors at the top of the comment section. Right, it's time to go back to school. I'll keep this short, I promise. Okay, let's have a look at some schoolboy physics. Now, I must admit, I have used some of this stuff during my career. I used to do a lot of electrophoresis, so I had to understand volts and currents and what have you. Anyway, the first one is V equals IR, classic one from our school days, where V equals voltage, I equals current, and R is equal to resistance. Pretty sure if you did physics at school, you would remember this one. Next up, we have P equals IV, where P is power, which is measured in watts. I is the current, measured in amps, and V is the voltage, which obviously is measured in volts. Now, another one that sticks in my head from school days is I equals AVNE, and we don't really need that one, and I can't really remember what it stands for. It's something to do with current and area and electrons and number of electrons and stuff. Anyway, those are the main equations I remember from school. V equals IR and P equals IV. Okay, so that's the limit of my understanding of electricity in terms of volts and amps and watts and what have you. I said I'd keep it short, and that was the best I could do. But what about series and parallel circuits? And it's important that I understand these so that I can understand how and why the batteries are wired up in the way they are. Again, I'll try and keep this short. Okay, so let's have a look at series and parallel circuits, because it's important I understand this, because this is to do with how my batteries are wired up in the boat. So first, a series circuit. So here we've got two very badly drawn batteries with their positive and negative electrodes on them, and in a series circuit, positive connects to negative and negative connects to positive, and we have these in a row effectively. However, in a parallel circuit, we have positive connected to positive and negative connected to negative, and then the connection made to the circuit. So in a series circuit, they're in line, and in a parallel circuit, they are parallel. But what does this mean in terms of the voltage and the potential current for these? Well, in a series circuit, if I remember this correctly, the voltages add up and the current stays the same. Whereas in a parallel circuit, the voltage stays the same, but the current adds. So in the case of my narrowboat, let's say I've got a 12-volt battery at 110 amp hours, and I connect these in series, and in the parallel circuit I've got the same batteries, 12 volts, 110 amp hours, but this time connected in parallel. So therefore in the series circuit the output would be 24 volts because the volts add, but the amp hours would stay the same at 110 amp hours. Whereas in a parallel circuit the volts would remain the same at 12 volts, but in this case the amp hours would be added together to give 220 amp hours. And in the narrowboat, the batteries are in parallel. Therefore, the voltage stays the same, 12 volts, but the amp hours, the amp output from the batteries, is added together. So I take the 210s, and that gives me 220 amp hours. So that's why it's important to know the difference between parallel and series circuits. You want to make sure things are wired up correctly. Now, one of the ways I remembered this at school is with Lego bricks. With these Lego bricks, the long top is the volts and the side is the amps, the current. If the bricks are stacked on top of each other, you still have only one long top, so the volts stay the same. But you have a big drop, hence the amps are added. And this is a parallel circuit. The bricks are stacked in parallel to each other. If, on the other hand, I lay the bricks out end to end in a line, this is a series circuit. The distance along the top is increased, hence the volts are increased. There is a longer top, but the drop down is the same as for one brick, so the amps don't change. I know it's a slightly odd way of remembering it, but that's the way I remember it from my school days. Okay, so let's talk about batteries. A number of people in the comments on my videos have talked about the importance of looking after your batteries, not letting them get below 50% charge and making sure that your batteries are in a healthy condition. My batteries are housed in the engine room below the plank in front of you that you can see with the 3 holes in it. To the right of those holes you can see 3 switches. Those are my battery isolation switches, and the silver box on the wall I now know controls the charging of those batteries when I'm on the landline. So there are the batteries. There are 5 of them in total. There is a starter battery, that is the one on the right, and then 4 leisure batteries, each of 105 amp hours. Okay, so let's have a closer look at these batteries. On the left, I've got the 4 leisure batteries. These are each 12 volts and 105 amp hours. And if you remember from earlier, I said that the batteries had to be wired up in parallel. And you can see they're in parallel here because positive terminals are connected together and negative terminals are connected together. And then at the end, 2 wires go off into the boat to provide electricity. So these are 12 volts each and they are 105 amp hours. So as they are in parallel, that means that I've got a 12 volt system with a total of 420 amp hours. The battery on the right is the starter battery, and that is not connected in any way to the leisure batteries. This means that I've always got power, if the battery is charged, to start the engine. So that's the battery setup on the boat. So the leisure batteries connected in parallel give 12 volts and 105 amp hours each. So a total of 12 volts and 105 times 4, which is 420 amp hours. But batteries are just a store of energy. So how do I get the electricity into the batteries? Well, I have 3 ways. I can charge the batteries from the landline if I'm in a marina. I can charge the batteries from the alternator when the engine is running, and I can charge the batteries from the solar panels. However, keep in mind the batteries only give 12 volts and some things on board use 230 volts, so we'll have to step up the voltage using an inverter. And this also brings me to the 4th source of electricity on the boat, a 230 volt generator on the engine. I have 2 solar panels on the roof of the boat, and I must admit that I don't know a lot about solar panels. From the paperwork I got with the grey wagtail, they seem to be 2 165 watt solar panels, so a total of 330 watts. However, I'm not sure how that relates to anything else on the boat. The engine provides 2 sources of electricity. There is the alternator, which you can see in the picture here, and a generator. Both the alternator and generator work in similar ways in that they have a magnet that is rotating in a coil of wires, and this produces an alternating current. Both the alternator and the generator are driven by belts that attach to the flywheel. So there is a 12 volt alternator, and then there is a 240 volt generator, which provides 240 volts alternating current to the boat. Okay, so DC direct current, AC alternating current, so what? Time for a bit more schoolboy physics. Now, direct current provides you with a constant voltage, basically. On the narrowboat, it's 12 volts. It doesn't change. The batteries put out 12 volts. Alternating current, on the other hand, such as the current put out by the alternator and the generator, changes over time. With alternating current, the volts go up and down. So here is the 0 voltage line, and what will be happening is our voltage will be going up and down. Now on the generator, this is 240 volts output. So actually, technically, it goes higher than 240 volts, because if I remember correctly, the voltage is determined by something called root mean square. But couldn't swear to that. Anyway, with the generator, we're getting an AC, which means our voltage is going up and down, as you can see here on the graph. And it's varying between plus 240 volts, roughly, well, a little bit more, to minus 240 volts. And it's actually doing this 50 times a second, because the AC generator is putting this current out with a cycle of 50 hertz. So it changes every 50th of a second. So that's the difference between AC and DC. Now, another way to get electricity on my boat is via the shoreline, and this is most probably the easiest way to do it. So here you can see my shoreline plugged into a bollard at the pontoon where I am in the marina. There is a meter on it, and I run the cable down the length of the boat. And it's still coiled up as it was in the earlier videos. I still haven't got around to uncoiling this. And then that plugs in at the back of the boat. On the boat there is one key cabinet that contains a lot of the controllers. Now in here we have a lot of the electronic control components. We've got the big blue box, which I now know is the inverter, which takes the DC, the direct current, from the 12 volt batteries and boosts it up to 230 volts and 50 hertz alternating current AC. The black box below it is a galvanic isolator, which is to do with when you plug your shoreline in to make sure that your boat doesn't effectively turn into electrode and dissolve. So that's what's going on in there. I still haven't used the inverter because I've spent most of my time hooked up to the shoreline. So how does an inverter work? How does an inverter carry out the magical task of changing DC to AC? So DC, direct current, provides a constant voltage, and what we need is an alternating current. The circuit to do this change is actually quite simple and just involves 4 switches, arranged as shown on the screen. So we have 4 switches and an AC circuit. And by the use of these switches, it's possible to produce AC, an alternating current. Now, with all the switches opened, switches 1, 2, 3 and 4 open, we get no volts through the AC circuit. The electricity can't flow. If we close switches 1 and 3, electricity can flow. So here I'm showing it with arrows. I'm showing the closed circuit. And there we have electricity flowing. But this is still a DC. It's a set voltage. Now, if we open the switches again, and this time close switches 2 and 4, we get a closed circuit again, and our current can flow. So now with switches 2 and 4 closed, the circuit is closed and the current can flow through the AC circuit. And note, it's now flowing in the opposite direction. It's now flowing from right to left, whereas earlier it was flowing from left to right. So effectively, we've changed the voltage across that circuit. We've changed it from a positive down to a negative. Now, if we switch back to 1 and 3 being closed and 2 and 4 open, we revert back to the earlier situation. And all the inverter does is rapidly flick between these two states. It flicks between 1 and 3 being closed and 2 and 4 open, 2 and 4 being closed and 1 and 3 being open. And if you plot what's happening on this circuit, you'll get a graph that looks like this. The voltage will go up to a maximum and then suddenly drop down to a minimum, up, down, up, down, up, down. And of course, this doesn't quite look like a sine wave. It doesn't look like the sort of cycling that we would expect or we would want on an AC circuit. So how does the system solve this? How do we go from this square wave that we've got here to a sinusoidal, a sine wave? So how do we produce this sine wave? Well, here we've got the circuits with 1 and 3 switches closed and 2 and 4 open. and we would expect this sort of square wave when we open and close switches 1 and 3. So what the inverter does very cleverly, and this uses solid state switches, so there's no manual switching here, is it will close switches 1 and 3, but sort of then briefly open them for a short amount of time, close them, open them for a longer amount of time, close them, open for a longer amount of time, close them, and then shorten that closing and opening time down. And if we look at what we actually produce, it's a series of square waves, as you can see here. But if we take the average of each of those sort of small square waves, then that means if we plot that, we then get the sinusoidal curve. And that's what's happening in the inverter, is those switches are flicking very, very quickly. They're a solid state switch, and they flick like that. And then after 1 and 3 or 2 and 4 have finished their work, what we then do is switch over to the other switches to produce the negative curve with the same process. So that is how we're producing an AC from a DC. But how do we go from 12 volts to 240? Well, this is back to some good old schoolboy physics, and this is something called a transformer. The square in the middle, that is a sort of ferrous core, and we have a wire from the 12 volt circuit wrapped around it. As it's an AC circuit, as the current flows through it, it produces a magnetic field, and that is transmitted through the ferrous core. And on the other side of the ferrous core, we have another circuit, and this time the wire is wound around the core multiple times. So there's less coils on the left here in the 12 volts and more on the 240 volts. And so as the AC current flows through the 12 volt, it induces that magnetic field, which is picked up by the coils on the other side of the core, the 240 side, and that bumps it up to 240 volts. So that's what the inverter is doing. It's using rapid solid state switching to generate the AC current with the sinusoidal wave, and then it uses a transformer to take that 12 volts up to 240 volts. Absolute magic. Genius. Downside of this, of course, is that you lose some of the power of the system when you do this. So you might only end up recovering 70 to 80% of the power that you put into the system. Now, if I've got that figure wrong, please let me know in the comments. But that's what I've read, is you end up with about 80% of the power that you've put into the system. So that's what the inverter does on your narrowboat, or camper van even. Clever stuff. Now, the other mysterious box tucked away in this cupboard of electrical delights is the MPPT controller for the solar panels, which I must admit I don't know a great deal about at this point. Now in this corner I have the controls for the electric system on the boat. At the top here I've got a power management system. This is the 12 volt sort of fuse panel. I can control and turn on and off various 12 volt appliances and lights, etc. around the boat and reset them if they trip. And at the bottom here I've got the 230 volt AC distribution, and that has got 3 settings: 0, which is off; 1, which is the shoreline; 2, the inverter; and 3, the generator, because this boat has on its engine a 240 volt generator, so I can use that to produce 240 volt on board if I need to. Over here we've got another control unit, and that's connected to the solar panels on the roof and tells me what's going on with them. Now for me, the critical things are making sure the battery charges on when I leave the boat and it's plugged into the shoreline, but I would turn that off if I wasn't on the shoreline, and the information that comes out of this power management system. So what does this mean? What's going on with this? This is one of the critical bits of equipment, and it allows me to monitor how electricity is being used on board the boat. At the moment I'm connected to the shoreline, and what this is telling me is I've got 13.3 volts in the system. I'm on channel 4, which is a domestic amp hour counter. I'm in mute mode. I can put that into beep mode if I want to, and the system is using 0.3 amps. The 0 amp hours here is telling me that I'm not draining the batteries. I'm not using the batteries because the batteries are currently on charge over here, and as a result I'm not using power out of the batteries. So that's the critical thing to look at. So what happens to this if I change any of my electric settings? So what I'm going to do now is turn off the battery settings, and I'm going to disconnect the shoreline. Now with the shoreline disconnected, I'm at 12.9 volts and minus 4.9 amps. I'm still showing 0 amp hours because I'm not pulling much current on the boat. I've just got a few lights on and the fridge running. So I'm now going to leave this to run for a little while to see what happens to the readings on the power management system. Okay, this is with pretty much everything on board turned off, and I've got 12.8 volts and plus 0.8 amps going in, and those 0.8 amps are coming in from the solar panel, and I can see that on the solar controller. Now over here I have information from the solar panels. As you can see, I'm pulling 14.32 volts, 0.7 amps, and that's going into the battery at 12.7 volts and 0.8 amps. Now this over here is telling me that I'm not using any power, and that's kind of curious. Now when I turn the inverter on, a little light lights up on this panel telling me the inverter's on, and I can then move the switch to inverter on the 230 volt supply, and the system will now be using the batteries via the inverter to power any 230 volt systems I've got on board. And having done that, we can see that we've dropped from the positive value that we had earlier of 0.7, 0.8 of an amp to a minus value of 1.1 amps, because the inverter, even though there is no 230 volt systems on in the boat at the moment, the inverter is using power in its own right to do the conversion. So we are pulling ampage out of the batteries. I will now leave this to run and see if we can get a amp hour recording. The amp hour value tells us how many amps we're using over the hours. I know how many amp hours I've got in the batteries, and I don't want to go below 50%. So I need to take that amp hour value for the batteries, which I'll calculate shortly, and then sort of say, right, 50% of that I can use. So that hour rate, that amp hour value there, shouldn't go above that value. If it does, then I need to sort of start the engine to recharge the batteries or connect the landline. So I did cover this earlier. I've got 4 leisure batteries, each of 12 volts and each of 105 amp hours. So that means in total, because it's a parallel circuit, it's 12 volts, and you add the amp hours together and that gives you 420 amp hours. So ideally, I don't want to take out more than 210 amp hours, 50%, from the batteries. Okay, so I've now been around the boat and turned on pretty much everything that I can find, including the electric water heater. And as you can see, I'm now pulling 112 amps out of the system, and I've already run up 3 amp hours of use, and that is in just a matter of minutes. Having everything turned on like that is something you would never really do, because it's a very heavy load on the system. On the boat, I have 4 105 amp hour leisure batteries which are connected in parallel, and so give 12 volts and 420 amp hours, 4 times 105. If you accept the 50% rule of discharge that I mentioned earlier, then I would have reached that 220 amp hours in about 2 hours. That gives you a real sense of why it's important to monitor electric usage when running on batteries. 2 hours is not very long. Okay, so I've now been connected up to the shoreline for a little while. I've still got 6.1 amps going in, 14 volts, and my amp hours have now dropped to -2. As the battery is fully charged, this will return to 0 when they are at the fully charged state. So if I was to disconnect the shoreline now and use the battery system, that number, that -2, would start to increase again. Well, decrease, it would get larger in terms of being a minus number, if that makes sense. Anyway, so that's what's happened after about an hour or so of being on the shoreline. I'm basically replenishing the batteries, and so my amp hours are being decreased. Well, sorry, same pun again, a hash I made of that. In the end though, I think I got there, but there were a few mistakes along the way. Did you spot any that I didn't catch in the editing? If you did, please leave a comment below and I'll add the correction to my pinned comment at the top of the comment section. Okay, so thanks for watching for this long. On the screen now you can see a QR code that will take you through to the Grey Wagtails newsletter. There is also a link in the description for the newsletter below. If you have enjoyed this video or found it useful, please give it a like. And if you haven't done so already, please consider subscribing. Again, thanks for watching. Bye for now.